Now that we have seen the basic principles of process control, let us set up a process control chart for my coffee machine. First, I collect observations over a 2-week time period to determine the normal behavior of the machine. Each day, I note the temperature of 9 random cups of coffee. During that 2-week time period, I watch the machine closely to make sure that it is, in fact, behaving normally. Here are the observations. For every sample of 9 observations, that is x1, x2, x3 up till x9, I calculate the mean, or Xbar. It is these Xbar values that I'm going to plot on a chart, so I call the chart an Xbar chart. To get the center line of this Xbar chart, I calculate the mean of the sample means, or X double bar. As expected, this number works out to 160 degrees, the center line of my process. Next, I calculate the process standard deviation, sigma process, which works out to 2.0 degrees. I use that value to calculate the sampling standard deviation, sigma sample, which works out to 0.667 degree. Note here how I got my sample size. I have 14 samples, but that is the number of samples, not the sample size. If I look at each sample, how big is it? Each sample contains 9 observations, so the size of each sample is 9. Based on this sigma sample, I can calculate the LCL and UCL of the Xbar chart to be 158 degrees and 162 degrees respectively. To plot the process control chart in Excel, I need to plot the numbers in the Xbar column and then draw 3 lines on the chart, the mean or X double bar, the LCL, and the UCL. It is easy enough to put down 3 extra columns of data in my table and plot those along with the Xbar column. Selecting all 4 columns, I can insert a line chart that plots the Xbar, X double bar, LCL, and UCL values together. I need to now double-check my chart to see if the process was in fact behaving normally during my data collection period. If there was some abnormal behavior during this period, it would make no sense to set this LCL-UCL band as representing normal behavior. Checking for non-random behavior, we can see that there are no runs or trends present. About 2/3 of the points lie within the mean plus or minus 1 sigma sample band. Over 95% of the points lie within the mean plus or minus 2 sigma sample band. All the points lie within the mean plus or minus 3 sigma sample band. Therefore, the process does seem to have been behaving normally during this 2-week data collection period. I now have confidence that these numbers I have calculated, mean or X double bar, LCL, and UCL, can be used as benchmarks out into the future. I can compare future samples against these benchmarks to see whether the process is still behaving normally. In the method we have discussed so far, I am using a single chart to look for shifts in the process mean as well as in the process variability. We can also plot 2 separate charts, an Xbar chart to monitor the sample means and an S chart to monitor the standard deviation. In fact, we typically need to first look at the S chart to ensure that the process variability is in control, because without doing that, what looks like normal behavior on the Xbar chart could be deceptive. Just in case you're wondering, recall from stats that S is the symbol for sample standard deviation, while sigma is the symbol for population standard deviation, which in our case is sigma process. Don't confuse that with the sampling standard deviation, which is sigma sample. Now, if our sample sizes are relatively small, say less than or equal to 10, an easier alternative to the S chart is an R chart. In this chart, rather than the standard deviation, we use the sample range, that is high minus low, to inform us about the process variability. To plot the Xbar and the R charts, I start out as before with my observations. For each day's sample, this time I calculate 2 numbers, the sample mean Xbar, and the sample range R. The Xbar values will be plotted on the Xbar chart, and the R values will be plotted on the R chart. The center line for the Xbar chart will be the mean of the sample means, or X double bar. Likewise, the center line for the R chart will be the mean of the sample ranges, or R bar. But without the standard deviation, how do I get the UCL and LCL? For that, I have to refer to these standard tables, which are also given in the textbook. Corresponding to our sample size of 9, I look up three values from the table. A2 equals 0.337, D3 equals 0.184, and D4 equals 1.816. Using these values, I can calculate my control limits using the formulas shown. In these formulas, I just substitute the values of X double bar and R bar, which I have calculated, and A2, D3, and D4, which I got from the table. Going back to my Excel spreadsheet, here are the values from the table. I then calculate the control limits for the X bar and the R charts. I can now plot my two control charts and monitor my process over time. Looking first at the R chart, we see a little suspicious behavior. My process variability does not seem to have been behaving normally during the data collection period. Although my sample mean appears to have been behaving normally according to the X bar chart, I cannot confidently use any of the control limits I have calculated, as they do not represent normal behavior. I will have to collect data again. Next time, I will watch the process more closely to make sure that all aspects of the process remain normal.